All right, B's and G's, welcome back to the drive-thru. Hope everyone's having a wonderful morning. As always, the drive-thru is sponsored by the deli. Hungry? Stop by the deli. Get yourself some delicious snack mix. This is 3-8, the HL postulate. Quote of the year so far by Johnny Hepler. It's like cheating, only it's allowed. All right, so what this is the fourth shortcut. So the ones we have right now before this lesson are SAS, SSS, and ASA, and now we're going to add to that the HL. What? HL? Well, we'll have to kind of go into some vocabulary involved with right triangles to explain what HL stands for. Here's the wordy version of the theorem. This is the HL theorem right here. Sorry, the HL postulate. No, why is it a postulate? We can prove this thing. I think we prove it using other postulates, so it must be a postulate. Okay, if two triangles are right triangles, if they have congruent hypotenuses, or hypoteni, not sure what that word would be, and they have one congruent leg, then these two triangles must be congruent to each other. So let's try to visualize that here. Let's say we've got some right triangles. Now, remember, the hypotenuse is the largest side of a right triangle. That's the definition. You've learned that before. The legs are the sides that make up the right angles. This can be confusing because some people also refer to legs as the sides of an isosceles triangle. So that can be confusing. I feel for you. Oh, geez. In use. Okay. So what this says is that if we know something's a right triangle, so what makes something a right triangle? It has to contain a right angle. And we know that the hypotenuse of one triangle is equal to the hypotenuse of another. How do we know something's the hypotenuse? It is always across from the right angle. That's why you're learning that now. Remember how yesterday in class you learned that the biggest side of a triangle is across from the biggest angle? And if you have a 90-degree angle in a triangle, it has to be the biggest angle. Think about it. So that's why we're learning this today. Well, if you also know that one of the legs of one triangle are congruent to one of the legs of the other triangle, now you can say that these triangles are congruent by the HL postulate. This is a specific version of the ASS theorem. Exactly. Look, this is ASS. But the ASS doesn't always work. It only works if the angle is a right angle. And at some point in your careers, particularly when we learn sine and cosine, then I'll be able to drop some of that knowledge on you, but not yet. I can't yet explain to you why ASS doesn't work. But in this scenario, it will always work. Love it that you picked that up. That's great. So, let's say we're given that NO, this is kind of hard to see, NO is perpendicular to OW, that NE is perpendicular to EW, and that NO is congruent to OW. Could we now prove that AB, sorry, not AB, prove that NW bisects angle OWE? Angle O. Could we prove that? Well, let's see how we would do that, okay? Let's label everything we have. We only know that that is that. Okay? We can say that angle NOW and angle NEW are right angles, new and now, and that's the definition of perpendicular. Okay? So now let's label that. So now it's apparent that our triangles are right triangles. In my class, you do not need to state that they are right triangles, because we've just stated that they're right angles. So I've got that one of the legs of the top triangle is congruent to one of the legs of the bottom triangle. In order to use HL, I need to show that their hypotenuses are the same. Well, luckily, NW is the hypotenuse. It's the side that's across from the right angle. And I know that NW is congruent to NW because of reflexive. So now you can see I've got the H part, I've got the L part. So now I can say that triangle now is congruent to triangle new. And my reason would be HL postulate. Yes, sorry. The given, I wrote the given wrong. NO is congruent to NE. Thank you. Just wrote that down wrong. Very good. So, we want to prove that NW bisects some angles. So then we've got to say that angle OWN, angle OWN, who would have thought that OWN would have produced so many different words? It's like an anagram. Angle OWN is congruent to angle UN, EWN, by CPCTC. And now I can say that NW bisects angle OWE, and that is the definition of bisect. All right, welcome back. Another proof here, okay? So, in this proof, we're given that SC is an altitude of circle S. So that means that S is the center of the circle. That's all we're given. And now we want to prove that IC is congruent to AC. All right, so all we know is that SC is the altitude of circle S. Well, that means that angles SCI and angle SCA are right angles. And that's my definition of altitude. So now I can mark my right angles because I've stated them. Well, SI is congruent to SA because all radii of a circle are congruent to each other. All right, those are my H's. They are across from the right angles. I need an L. I need to show that that one of my legs from my triangle on the left is congruent to one of the legs from the triangle on my right. Well, luckily, SC is a leg in both. And it's congruent to itself by reflexive. So now I have enough information to show that triangle SIC is congruent to triangle SAC. And that's by the HL postulate. So, IC is congruent to AC, notice, by CPCTC. CPCTC. Can I get a boom for us, Bill?